Hi folks. In this presentation, I'm going to talk about solder in the context of hand soldering. I'm going to cover some of the different alloys, some of their properties and characteristics, and some of the applications that these solders are used on. I hope that you find the information informative, and I hope that it gives you a better understanding of these materials, which hopefully will allow you to make more reliable and better quality solder connections. Thank you.
I would first like to talk about operator safety. Whenever you handle materials that contain lead, you need to wash your hands thoroughly afterwards so there's no danger of ingesting lead. You can also wear nitrile gloves, which are also anti-static, when handling materials that contain lead. Of course, if you're using lead-free solders, it's not really a problem. Conversely, human skin is slightly acidic, so it's advisable to wash your hands before you solder as well, so as not to contaminate the project being soldered with oils or other contaminants. Also, if you use hand creams, use electronic grade hand creams, as they do not contain silicone or lanolin, which could also contaminate the materials that you're soldering. So the best practice is to wash your hands before and after soldering. Now, the good electrical and mechanical properties that we get from solder are provided by a process called wetting. So the tin in the solder dissolves whatever the base metal is. And that's where we get our mechanical and electrical connection from. And that connection is called an intermetallic bond. Now, since we're talking about soft soldering here, soft soldering is soldering with solder that melts under 850 degrees Fahrenheit. So the metals that we're using, the solder, is a relatively soft and malleable material. Therefore, it's not a highly structural material. The two materials that we're going to be soldering together need to be in relatively close proximity to each other, approximately 3/1000ths of an inch, in order for us to get that intermetallic bond to work for us. Now, no discussion about soldering would be complete without defining the term eutectic. A eutectic alloy is one that refers to compounds or elements which contain two or more metals but behave as if they were a single metal. That is, these alloys exist only in two states, solid and liquid. Whenever a solder alloy is not eutectic, and you can see this by a melting temperature range being specified, the alloy has a third state called a plastic state or pasty phase, where the solder is neither solid nor liquid but in an in-between plastic state. In this tin lead diagram example, you can see that the binary 6337 alloy melts at only 361 degrees Fahrenheit, while the 5050 alloy has a melting temperature range of 361 to 414 degrees Fahrenheit. The 5050 alloy is referred to as a wiping alloy for soldering stained glass windows or other metal seams. As you are drawing solder across the seam, the solder will remain in its molten state where it can cool into one smooth continuous bead. The reason I'm mentioning all of this is to tell you that it is critical with non-eutectic solders that the solder joint be allowed to cool undisturbed. Eutectic or near eutectic alloys are less susceptible to cold solder joints and are primarily used for electronics related applications. I've also included two charts here just for your information that give you the melting temperatures of the various metals and also a couple of different alloys that are commonly used nowadays in solder. The interesting thing to note is that the melting temperatures of the final solder alloy is lower than the melting temperature of the individual metals that are contained in that alloy. And here are two examples of that in this diagram. This chart that I have included for your information shows some of the different soldering alloy families. There are over 150 known solder alloys in temperatures ranging from 117 degrees Fahrenheit to 850 degrees Fahrenheit. Now, many of these alloys, not all of them, are available in many different diameters from 0.004 of an inch up to about 1/4 of an inch in solid wire form
for use with external flux, or flux cord versions across a different range of flux chemistries. In choosing a wire solder diameter, a general rule of thumb is to choose the diameter of solder that enables you to use approximately 3/8 of an inch per connection, as finer wire diameters are more expensive. The most common tin lead alloys used are 6337, that's tin lead, 6040, and 5050 for stained glass and for soldering copper seams. The most common lead-free alloys are what are called, one is called SAC 305, which is 96.5% tin, 3% silver, and 0.5% copper, as well as SN 100, which is 99.3% tin, 0.7% copper, and 96.5% tin, 3.5% silver. Now, speaking of lead-free alloys, all of the electronic and electrical products that we buy and use today are made with lead-free materials. This is due to a directive initiated by the European Union in 2002 called the Restriction of Hazardous Substances, or RoHS for short, which is meant to greatly reduce the environmental impact of lead, cadmium, and other materials from accumulating in landfills. Now, be aware that these lead-free alloys behave differently than tin lead alloys. Melting temperatures are higher, the solder has a higher surface tension, and does not flow as easily as tin lead. It also has a greater ability of dissolving copper and iron-plated soldering tips because of the high, greater than 92% tin content. These materials are typically more challenging to use, and the solder joints tend to be heavier and more grayish and grainy in appearance, so we must be aware of this and must learn how to make and inspect these connections. Something else that I need to mention here that's very important: do not mix different solder alloys on the same project, as unpredictable results may occur. For example, if you mix a tin lead alloy with a lead-free alloy, the melting temperature will change and the solder joint will be severely weakened. For those of you that may be soldering fine copper wire, like for coils, transformers, guitar pickups, other applications, we need to use a solder alloy designed for that application. Since we know that tin readily dissolves copper, when we attempt to solder fine copper wire, we will greatly reduce the cross-sectional area of the wire and severely weaken the wire at the point where it exits the solder joint. Therefore, we need to use a low tin, high lead alloy like 1088-2, tin lead silver. It has a higher melting temperature, but it will not dissolve a significant amount of copper. This alloy that I mentioned and the one I have listed on this slide are exempt from the RoHS directive that I just talked about, since this is really the only way to solder a fine copper wire. Thank you again for your interest. Let me know if I could be of any assistance. Thank you.